So the difference between elastic and plastic section properties are very important when we study structural steel design. And that has to do with the different resistance and moment for various shapes under various conditions of loading, either yielding or ultimate condition. Now, if we look at the steel handbook, we would see properties of shapes, different, in this case it's W shapes, and we could go to the handbook and pick off a moment of inertia and values called section modulus, elastic section modulus, and a plastic section modulus. And the magnitude of the section modulus allows us to directly calculate moment. And elastic allows us to calculate yield moment, whereas the plastic allows us to calculate the ultimate moment of the section. Now it's important to understand where those come from, so we'll go through a few different examples today and see the development of the section properties for both elastic and plastic sections. So our first example, we would take the most basic thing we could imagine, which would be a rectangle here, and it would be of width B and of height D. And we know that this rectangle would have a neutral axis that would be at exactly D over 2. Let's call that Y, and it would be the same value here, Y. And in the middle here, we could draw our X and our Y axes if we wished. Now, if we went ahead and put a moment on this particular member, we would see, or this section, we would see that extending this neutral axis out, we could draw our strain diagram. And the strain would pass through 0. It would be a linear stress or a linear strain distribution, according to a plane strain assumption that we use in steel design. It would have a strain at the top, epsilon top, and let's say that that for now is less than or equal to epsilon y, which would be yield strain. And it would have a strain at the bottom, and that's also equal or less than or equal to yield strain. Now, if our material property happens to be elastic, perfect plastic here, so here we would have strain and stress, and we'd have a yield strain and a yield stress Fy, and down here we would have our moment of, or our Young's modulus, our elastic modulus for that. Now, if the strain at maximum strains at the tips of the extreme fibers on this section are less than or equal to yield strain, that means that all the strain is less than yield strain, and if it's that case, it's a linear relationship. So our stress as well will be linear over the section. In other words, if let's say we found strain here is that value, we could find the corresponding stress as that value. And that would give us a stress for the top is less than or equal to Fy, and a stress for the bottom is less than or equal to Fy. So this is our basic elastic stress strain sectional analysis stuff. If we looked at what was happening internally here, we could say that that moment put a stress and there's a resultant force from that stress. This is force at the top, we'll call it Ft, and there's this corresponding force at the bottom, Fb, and they're located a certain distance away from the neutral axis. Well, let's call that Yb for Y bottom and Yt for Y top. We know that the value here, Y itself, is at D over 2 for that simple rectangular shape. And this would be the neutral axis location. Now, we also are able to directly calculate the force in the top and the force in the bottom. First of all, let's look at that section and let's apply equilibrium. So sum of forces has to equal to 0. And this means that we have force in the top, and I drew it as going this way, has to equal to force in the bottom, which I drew as going that way. So they're the same magnitude as the only two forces on this section. The value of force, or force at the top, is simply equal to the stress at the extreme fiber multiplied by y times the width, all divided by 2. So it's the area under this triangle multiplied by the width of the section. And this is also equal to force bottom, as we said, and just through our equilibrium. Now we can go further to that, and let's find the y top value. And to do that, let's just draw this little triangle out here. This is the stress distribution at the top, and we know we have y. And here would be our centroid, and we know that that is simply 2/3 y is equal to yt. So we found that value there. And now we also note that this is also equal to yb. The moment itself, m, so if we take the sum of moments and set that equal to 0, we would have moment, as I drew it, I applied it going in the clockwise direction, and that would simply be equal to force at the top multiplied by its moment arm, y top, which is going in the counterclockwise direction, plus force at the bottom multiplied by y bottom going in the counterclockwise direction. This equates to 2ft yt based on yb and yt being equal, and fb and ft being equal. So we could expand this out and say moment is equal to 2 ft, we already defined as sigma t y b over 2, multiplied by y top, we've defined as 2/3 y. And since y is simply equal to d by 2, we could rewrite this in that terms and find that moment is equal to 2/3 stress multiplied by d over 2 squared times b. And this is equal to, moment is 1/6 stress bd squared. So we found that through first principles in equilibrium. We found this moment value. And we also knew something else. We could have started this instead and said that moment is simply equal to stress times I over y. And this is, you might know that more as stress is equal to my over I. And the derivation of this little equation is done exactly how we did this calculation up there. So realistically, if we kept y is the variable, the distance from the neutral axis to the extreme fiber, and then we converted this into moment of inertia, we'd get the same equation. So we can verify that quite simply. We know that I is equal to 1/12 b d cubed, and this gives us moment is equal to stress times 1/12 b d cubed over y, which is d over 2, and this is equal to 1/6 stress b d squared. So we found our elastic moment for this section, and that was nothing too difficult. Now let's define something new though, or new to this example at least. Let's define elastic section modulus. And this is a material, or not a material, a section property, a property of the shape. It's like moment of inertia is a property of the shape. As long as the shape is linear elastic, this has to do only with geometry. And this is known as S, which is equal to moment of inertia over y. So it's simply the moment of inertia divided by the distance to the extreme fiber. And for this section, S in the x, we have a moment of inertia about the x-axis, we have a section modulus about the x-axis, is equal to the moment of inertia about x over y, and it turns out to be equal to 1/6 bd squared. So we found our elastic section modulus. Now what happens if this section was to plastify? In other words, if we flip back here, what would happen if we were to push the extreme fiber stress beyond yield all the way over into plastic and then well beyond, to the point that the entire section has plastic strain and plastic stress? Let's see what we get with that. Well, first, before we do that, let's just go one step further. If we found before that moment of inertia was equal to a stress times I over y, and we redefined I over y, we can now say that yield moment is equal to yield stress times section modulus. And this is what we'd use in the steel design code. We'd actually apply material factor as well. Or in more general terms, moment is simply equal to section modulus times stress. So that's if you are less than yield stress. Let's go to the plastic properties here. Plastic section properties. Now here we're going to be interested in stressing this and straining it as far as it will go. So if we start with the same section here, a rectangle of the same width b and of the same height d, well, we know that the neutral axis remains in the middle here, and we're applying a moment here. Let's call this a plastic moment now, and we have distance is y to the neutral axis, in this case the plastic neutral axis, and we strain this thing, and strain remains linear no matter how plastic we go. This is this plane strain remains plane assumption. We get strain at the top is much, much greater than yield strain. Strain at the bottom is also much, much greater than yield strain. And then we can approximate our stress as two rectangular stress blocks, both of magnitude Fy. In other words, the strain everywhere along this curve is somewhere in this region with the corresponding stress of Fy. And that gives us simple internal forces of F top and F bottom, and they are located at Y top and Y bottom. But we can solve for this fairly simply. We can say that sum of forces has to equal 0, and this means that F top has to equal F bottom. And if we want to calculate one of these, we could say F top is equal to the stress multiplied by the area of this rectangle, Y, multiplied by the width. So stress Fy times the height gives us the area of this shape, multiplied by the width gives us the total force across that width. And then we can also say that's equal to F bottom. And finally we could say Y top is equal to Y bottom, as the centroid of this rectangular shape is simply equal to Y over 2, which is equal to D over 4. So now that we've defined the forces and their locations, we can take the sum of moments about the neutral axis location and set that equal to 0. And this gives us MP, which I drew is going that way, has to be equal to F top multiplied by Y top, which is going the other direction, plus F bottom multiplied by Y bottom, also going the other direction. And this is simply equal to 2 F top Y top, since F bottom and Y bottom are equal to F top and Y top. And if we complete this, we end up with 2 times the stress times Y. So here we're plugging in the value for f top times b multiplied by y top, which is y over 2. And this computes out to be equal to yield stress multiplied by y squared b. And if we substitute d values for y is equal to d over 2 into this, we can get m plastic is equal to fy d over 2 squared b, which is equal to 1/4 fy b d squared. And this is MP. So we've calculated the plastic moment resistance of this section. Plastic meaning the whole section has gone beyond yield. Now let's go a step further and work on introducing a new factor, or new property. Let's define plastic section modulus. And this plastic section modulus is called Z, and we can define it as our plastic moment divided by Fy. And it's also a property of the shape, not a property of the whole member. It doesn't have to, the member length or anything doesn't really matter. It's a shape property as long as the material is elastic, perfect plastic. And in our case, we can generally have Zx or Zy, so Zx is mpx over Fy. And for our shape, this gives us, by the way, we can rearrange this. We can say moment plastic is simply equal to Zx Fy. So that's the power of that Z value. We could simply find our plastic moment right away by looking up the section property in the tables rather than go through this effort. Now for our shape, we had Z was equal to MP over Fy, which was 1/4 Fy b d squared over Fy. So Z was equal to 1/4 b d squared. For this particular shape, this is shape dependent. This is for our shape only. We'll see later that other shapes have different section properties. Now, once we have this value, it's interesting to note the relationship between this and the elastic section modulus. So let's recall that we had S was 1/6 b d squared, also for our shape. And this brings us to something else. Now we can introduce something called a shape factor. So let's define shape factor. And this shape factor is a comparison between elastic and plastic material properties. And it allows us to sort of optimize the shape of the section that we will choose. Is there a major difference between a rectangular section and an I-beam section, or a channel section, or a T section? The shape factor allows us to make that decision in a rational way. So shape factor K is simply equal to Z over S. And in our case, we had K is equal to 1/4 BD squared over 1/6 BD squared. And K is equal to 1.5. And if we look back at how we calculate moment, moment is the section modulus times a stress, we can say that this would allow us to directly compare moments. So in this case, the plastic moment capacity is 1.5 times higher than the elastic moment capacity for a rectangular section. So the next video in this small series will bring us into the similar calculations for an I section instead of a rectangular section, and we'll start to see variation in this K factor. The final video will bring us into a non-symmetric shape where we get a shift in the neutral axis, and how we deal with that once we get to plastic neutral axis, where the member behaves differently than under elastic bending.